The sun, it's a giant ball of plasma. It's the heart of our solar system, and it's the reason we're all here. Literally, the sun is a yellow dwarf star about 4.6 billion years old. That's roughly the same age as Earth. This massive star stretches 865,000 miles across, which is more than 100 times Earth's diameter. The sun is also incredibly heavy, containing 99.8% of the total mass in our entire solar system. Located about 93 million miles from Earth, the sun bathes us in light and warmth. Its surface temperature is a scorching 10,000 degrees Fahrenheit, but the core, that's where things get really interesting. The sun's core is a nuclear furnace with temperatures reaching 27 million degrees Fahrenheit. It's here that the magic happens, literally magic, or at least what we used to think was magic. The sun is mostly made of hydrogen and helium. These elements are constantly colliding in the core. This collision, under immense pressure, causes nuclear fusion. Hydrogen atoms fuse to form helium, releasing an incredible amount of energy in the process. This energy powers the sun. It radiates outward, eventually reaching Earth as sunlight. It's this energy that drives our weather, fuels plant life, and, well, keeps us from freezing in the dark depths of space. Thank you, fusion. The sun isn't just one big ball of fire, it's a complex structure with distinct layers, each playing a crucial role in generating and transporting energy. The core, as we've discussed, is where the fusion party happens. Surrounding the core is the radiative zone. Here, energy slowly travels outward in the form of photons, bouncing around for thousands of years. Talk about a long commute. Next comes the convective zone. Here, hot plasma rises, cools, and sinks back down, creating a churning motion. Think of a boiling pot of water, but on a much grander scale. Finally, we reach the sun's visible surface, the photosphere. This is where sunspots, cooler regions caused by magnetic activity, appear. The sun isn't always calm and predictable. While it may seem like a constant, unchanging ball of light in the sky, the sun is actually a dynamic and ever-changing star. Its surface is a roiling sea of hot plasma, constantly in motion and full of surprises. It can throw some pretty impressive tantrums, known as solar storms. These storms are not just random events, they are the result of complex processes happening deep within the sun's core and its outer layers. These events are driven by the sun's magnetic field, which can twist and snap, releasing bursts of energy and particles. The sun's magnetic field is incredibly powerful and intricate, with lines of magnetic force that can become tangled and then suddenly release, causing solar flares and other phenomena. One type of solar storm is the solar wind. This is a continuous flow of charged particles, primarily electrons and protons, that stream out from the sun in all directions. The solar wind is always present, but its intensity can vary. This constant stream of charged particles flows from the sun, impacting Earth's magnetic field and creating beautiful auroras. These natural light displays, often seen near the polar regions, are a direct result of the interaction between the solar wind and Earth's magnetosphere. But solar wind can also disrupt satellites and power grids. The charged particles can interfere with the electronics on satellites, causing malfunctions or even complete failures. On Earth, the solar wind can induce currents in power lines, potentially leading to power outages. Then there are solar flares, sudden bursts of radiation from the sun's surface. These flares are the most powerful explosions in the solar system, releasing as much energy as billions of hydrogen bombs. These intense flashes can interfere with radio communications and pose risks to astronauts. The radiation from a solar flare can disrupt the ionosphere, affecting radio signals and GPS systems. For astronauts, the increased radiation levels can be dangerous, requiring them to take shelter in shielded areas of their spacecraft. Coronal mass ejections, or CMEs, are even more dramatic, hurling billions of tons of plasma into space. These massive bursts of solar material can travel at millions of miles per hour, carrying with them a magnetic field that can interact with Earth's own magnetic field. If a CME hits Earth, it can trigger geomagnetic storms, disrupting power grids and causing widespread blackouts. These storms can also affect navigation systems, satellite operations, and even pipelines. The impact of a CME on Earth can be far-reaching, highlighting the importance of monitoring solar activity and preparing for potential disruptions. Like all stars, the Sun has a life cycle. It was born from a cloud of gas and dust known as a nebula, which collapsed under its own gravity. Over millions of years, this material coalesced to form our Sun. It wasn't always shining, and it won't shine forever. The Sun's journey from birth to its current state has been a long and fascinating one. Right now, the Sun is in its main sequence stage, happily fusing hydrogen into helium. This process releases an immense amount of energy, which is why the Sun shines so brightly. This phase will last for billions of years. During this time, the Sun remains relatively stable, providing the energy necessary to sustain life on Earth. But eventually, the Sun will run low on hydrogen fuel. As it depletes its hydrogen reserves, the core will contract and heat up, causing the outer layers to expand. When this happens, it will enter its red giant phase. The Sun will swell to many times its current size, becoming a red giant. The Sun will expand dramatically, engulfing Mercury and Venus, and possibly even Earth. The intense heat and radiation will make life on our planet impossible. Talk about a bad day on our planet. The transformation into a red giant will be catastrophic for any remaining life on Earth. As a red giant, the Sun will fuse helium into heavier elements. This process will continue for a relatively short period compared to its main sequence stage. Eventually, it will shed its outer layers, creating a beautiful planetary nebula. The outer layers will drift away into space, leaving behind the core. This stellar remnant, known as a white dwarf, will slowly cool and fade over trillions of years, marking the end of our Sun's life. The white dwarf will no longer undergo fusion, and it will gradually lose its heat and luminosity, becoming a cold, dark object in the vastness of space. The Sun is more than just a star. It's the lifeblood of our solar system, providing the energy necessary for life on Earth. Plants use sunlight for photosynthesis, producing oxygen and food that sustain the entire food chain. The Sun's gravity keeps Earth in orbit, preventing us from hurtling off into the vastness of space. Its warmth drives our weather patterns, ocean currents, and climate. Without the Sun, Earth would be a barren, frozen wasteland. But the Sun's influence extends beyond Earth. It's a crucial factor in space exploration, providing power for spacecraft through solar panels. Studying the Sun helps us understand space weather, which can impact missions and astronauts. By learning more about our star, we can explore our solar system safely and efficiently. The Sun is our closest star, a blazing ball of gas that has fascinated humanity for millennia. Its immense power and energy are the very foundation of life on Earth. It serves as a giant laboratory for understanding the universe. By studying its composition, we can unravel the mysteries of stellar formation and evolution. The Sun's structure, with its core, radiative zone and convective zone, provides a blueprint for other stars. Its behavior, including solar flares and sunspots, offers clues about magnetic fields and plasma physics. By observing the Sun, we gain insights into the workings of other stars and galaxies. The knowledge we gather helps us understand the life cycle of stars, from their birth in nebulae to their eventual demise. Solar observatories, both on Earth and in space, constantly monitor the Sun. These observatories are equipped with advanced instruments that capture high-resolution images and data. Scientists analyze this data to reveal the Sun's secrets. They study solar cycles, magnetic field variations, and energy output to predict solar activity. We learn about the Sun's magnetic field, which influences space weather and affects satellite operations. The solar wind, a stream of charged particles, interacts with Earth's magnetosphere. Solar storms caused by eruptions on the Sun's surface can disrupt communications and power grids on Earth. They also create stunning auroras, lighting up the polar skies with vibrant colors. This knowledge helps us predict space weather, which is crucial for protecting our technology and infrastructure. Satellites, power grids, and even airline routes can be affected by solar activity. Understanding the Sun's behavior is also vital for the safety of astronauts. Space missions must account for solar radiation and potential solar storms to ensure the well-being of those exploring beyond our planet. But the Sun's importance goes beyond practical applications. It inspires us, fills us with awe, and connects us to the cosmos. Watching a sunrise or sunset reminds us of the Sun's daily journey and its role in our lives. The Sun's energy drives weather patterns, supports ecosystems, and sustains life. By studying the Sun, we deepen our understanding of our own planet and its place in the solar system. We unlock not just the secrets of our star, but also the mysteries of the universe itself. The sun is a gateway to understanding the fundamental processes that govern the cosmos. As we continue to explore and study the sun, we uncover new layers of knowledge that illuminate the vast, intricate tapestry of the universe. Each discovery brings us closer to comprehending the grand design of the cosmos.
You need to watch this if you want to discover life's hidden gems. Join our channel for tips, tricks, and secrets to live your best life. Like and subscribe to start your journey today.